Hello, everyone. My name is David Bruns-Smith. I'm a computer science PhD student at UC Berkeley, and this talk will be about using supervised learning to estimate inequality in the size and also the persistence of income shocks. I'd like to thank my advisors and collaborators on this project, Avi Feller and Emi Nakamura. There's been lots of successful work at the intersection of economics and computer science, especially microeconomics in the fields of mechanism design and algorithmic game theory. But what about macroeconomic questions, like is fiscal stimulus less effective when households have lots of debt, or why is the racial wealth gap so persistent? That's led to my research agenda of asking what, if anything, can machine learning contribute to macroeconomics? In this talk, I'll be discussing one such line of research on income prediction and income uncertainty, where we define and measure income shocks by solving a time series income prediction problem. That prediction problem looks like this. We take past information and current income and then try to estimate future expected income in order to estimate income shocks and their persistence. We solve this prediction problem and measure income shocks in an Icelandic administrative tax data set. And I'd like to thank some folks at Statistics Iceland for their help with the tax data. The application I have in mind is the marginal propensity to consume. So here we have a household in 2022 that makes $60,000 annually. Then over the next year, two different things happen. There's an especially snowy spring construction season, which leads to a temporary negative $20,000 change. And also one of the household members is promoted to site manager, leading to a persistent plus $5,000 change for a net 2023 income of $45,000. We can then ask, this is what the marginal propensity to consume is, how does the household consumption respond to these income shocks? Do they spend less because of the temporary shock, or do they even default on their mortgage? Or because their permanent income has actually increased going into the future, would they spend more? The aggregate response is a key parameter for fiscal and monetary policy. And heterogeneity in the response matters for the evolution of inequality. There's a vast literature on this topic in economics and sociology, which we briefly review in the paper. There's two technical challenges here. Problem one is we observe income in 2022, we observe income in 2023. We don't know which part of the change is unexpected, and we also don't know whether or not the shock is temporary or it's persistent. And problem number two is then estimating how the consumption actually responds to these shocks. In this talk, we're going to focus on tackling problem one. So a typical approach to modeling income shocks is to specify a parametric linear AR1 model for permanent income. So you split income into a permanent component and a temporary component. But this is a narrowly defined parametric model, and there's no heterogeneity across households. So we take a different framing. We define persistence as a function of expected future income. This gives us a non-parametric definition of income shocks, which we'll illustrate next. So for each person, we see a trajectory that looks like this. We said their income at each age, maybe from age 30 to 54. And then we can think about the conditional expectation of future income given information known at time t. So if we condition on time t at age 32, we can look at the conditional expectation of income h years ahead into the future, where we condition on the all information known at time t. So that includes lag of income, but also gender, education, housing, wealth, etc. We then see actual income at time t plus 1, which is different than the expected value. And that difference we define as the total income shock. Now that we observe income at time t plus 1, we can update the information set and update all of the expected future income, those conditional expectations. The change to the expectation is what we define as the persistent shock. So in this case, there's a big positive shock at age 33, but only about half of that is expected to pass through to age 34. And the remainder we define as the transitory shock. The long horizon at, say, h equals 10 or 12 is informative of how persistent the shock is further into the future. So this gives us a non-parametric definition of income shocks and their persistence. All we need in order to compute them are these conditional expectations, and a conditional expectation is a best mean squared error predictor, which we know how to estimate using off-the-shelf machine learning tools. We go ahead and solve this prediction problem using Icelandic tax data. So we have access to administrative data for every individual in Iceland going back to 1980. For each year, we see individual income, wealth, and debt. Here's a picture of Iceland, which is the object of our study. We solved this future income prediction problem with features including current log income, lagged log income, housing and other wealth, demographics, calendar year, etc. And our prediction target is log income after H years. We used a variety of models, including linear regression, elastic nets, random forest, gradients, boosted trees, etc. So one question I had is, how well does the best performing flexible model, I think it was gradient boosted trees, compare to linear regression? Because, for example, the Fragile Families project found that in social science prediction class, low dimensional linear regression was actually really hard to beat in performance. If you look on the left-hand side here, for prediction 1 year ahead for upper middle class families and the income distribution, actually the linear model is pretty good. We only see around a 4 to 5% MSE improvement against the linear model. But it's really for the bottom of the income distribution, for the bottom 5 to 10% of individuals, that we see a big performance by using the more flexible model. Likewise, for 5 years ahead, the nonlinearities seem to matter more across the whole income distribution, but again, mostly for the bottom 5%. So we can ask, did we succeed at predicting future income? Did we do a good job at the prediction task? Well, since we're interested in the residuals, the absolute accuracy is not exactly the right metric. Since we want to approximate the conditional expectation, that's our goal, we only need the best accuracy relative of all functions of the input features. And so we want the distribution of prediction errors to be conditionally mean zero and as small as we can get them. Here I plot the quantiles of the prediction errors for the linear model on the left. You can see that we have a very sort of skewed, non-conditionally mean zero distribution of prediction errors, whereas on the right-hand side for our gradient boosting model, we have a consistent mean zero, symmetric residuals for our prediction errors as a function of current income. So I take this as validation that we have in hand a pretty good estimate of the conditional expectation. That means we can go on to actually construct income shocks. So for each person in each year, we can construct the total income shock, the difference between expected and actual income. And we can also calculate the shock persistent at each horizon H by computing the change to the updating the conditional expectation using the new information. So we can go back and revisit the quantiles of the prediction error, but thinking about them substantively as income shocks. And you can see, for example, that for the lowest income households, not only do they have low income, but they have much larger distribution of income shocks, meaning more income risk. We can also ask questions like, well, how persistent are these income shocks? So here I have a plot of the average persistence of shocks at horizon going out into the future. On average, somewhere around 35.8% of income shock persist after 1 year, but only 13.1% of income shocks on average persist after 12 years. So over time, there's a considerable amount of mean reversion. And being able to compute this persistence over time is one of the benefits of being non-parametric. We didn't have to specify beforehand with a parametric model exactly how persistence over time is supposed to work. We also see things like substantial asymmetry between the persistence of positive versus negative shocks. And what I'm plotting here are just averages. We actually get the heterogeneity and persistence over time with respect to all covariates, which is very powerful. So some of the takeaways, our methodology was to define non-parametric estimands for income shocks and shock persistence. We then just have to approximate conditional expectations by solving prediction problems to actually estimate these shocks, and this is easy to implement with off-the-shelf prediction tools. And by doing this in an actual data set, we find many facts about income risk that are incompatible with standard linear panel models. For example, we see much larger shocks at the bottom of the income distribution, a rapid nonlinear decay in persistence, and then wide heterogeneity and asymmetry of shock persistence. Also, coming soon, we should release estimates and analysis of income shocks using publicly available PSID data in the United States. Hopefully, this will be a good complement to the adult dataset for studying household income with machine learning. And once we have these shocks in hand, we can then go on to actually try to answer downstream economic questions. But there are many resulting technical challenges here, including causal inference, uncertainty quantification, etc. So that's an exciting direction for future work. That's it for the talk. Thank you very much, and please feel free to reach out if you're interested.